I'm sharing our research work here on active metasurfaces in space and time. So we're going to be discussing today about metasurfaces that are reconfigurable in their spatial configuration and also their temporal configuration and combinations of the two. So we'll begin by introducing the people who do the work. And I want to particularly highlight the work in this context of Prachi Thureja and Jared Sisler on space-time metasurfaces, of Claudio Hale, Ruzan Sequoian, and Morgan Foley on high quality factor metasurfaces, and Julie Belleville and Prachi Thureja on what I will describe as a new mode of active metasurfaces for imaging. So as you all know, we are in the midst of a flat optics revolution. This flat optics revolution is made possible by printable nanostructures that we can now make at scale. And they are replacing bulk optics in many applications and have potential to do much more. In addition to reducing the size and weight of optics, they also introduced the concept of multifunctionality, and that's illustrated on the right-hand part of my slide here, which illustrates work by both Andre Faron, my colleague at Caltech, and Federico Capasso, showing the concept of multifunctionality, where a meta lens is being used to focus, but each of the resonant elements is elliptical, so it has a different focal point in the far field for the two orthogonal linear polarizations. So combining a birefringent or beam splitting effect with a focusing effect. And so this is part of the broader arc of progress that we can identify in which metasurfaces are currently today. And of course, this builds on a foundation that goes all the way back to the 1970s, 80s, and 90s of the powerful electronic integrated circuits that power our phones and electronics and internet, and also the guided wave silicon photonic integrated circuits that were developed in the 2000s. A decade later, the whole field of metasurface optics began. And for purposes of today's presentation, I'm going to identify the metasurface optics that you're familiar with, where patterns are printed at the time of fabrication in a fixed fashion as a passive metasurface. And by contrast, we can identify an active metasurface in which each of the elements, resonant elements, is electronically reconfigurable. Such active metasurfaces represent powerful optoelectronic integrated circuits for computational imaging. So you can think about the entire progression of metasurfaces from what we can now think of as passive metasurfaces, first elements which acted as simple lenses or polarization converters, to those which combined components, to the first active metasurfaces that allowed us to reconfigure elements to produce, for example, a different amplitude or phase gradient, and followed by active multifunctionality, where a single active metasurface was reconfigured to perform multiple functions, to another concept we can think of as active multitasking, in which metasurfaces are modulated sufficiently rapidly that the frequency of light is now changed, and we can identify this as a space-time metasurface. There's a very nice new review, which was coordinated by Arseny Kuznetsov and Mark Bromersma, a beautiful review in ACS Photonics that appeared recently. It's an entire community effort summarizing the state of progress. And this graphic shows the state of progress in the area of active metasurfaces. So on the right, you can see that there are a variety of physical mechanisms that are used to produce the reconfigurable phase, amplitude, and polarization, including liquid crystal activation, thermal optic modulation, field effect tuning, and electro-optic modulation. And I've introduced the concept of quasi-static and now time-modulated metasurfaces. And we're also interested in metasurfaces that operate in either reflection or in transmission. And to date, many of them have operated in reflection mode, as I'll show, there's great interest in metasurfaces that operate in transmission mode as well. So in this talk, I'll begin by talking about metasurfaces based on a concept that we've worked on now for a number of years, in which field effect modulation of a conductive oxide near the epsilon near zero transition leads to very strong phase modulation. So each antenna is a resonant antenna at subwavelength dimension that localizes a magnetic dipole mode. And each antenna electrode also can be independently controllable to tune the permittivity and therefore the phase. And this can be done at relatively high frequencies, up to 50 to 100 megahertz, in principle also going to gigahertz frequencies. And that's been the basis for developing active multifunctional metasurfaces like this device that was reported in 2018 and in 2020 that allowed for active beam steering. This is an integrated circuit that was produced with 96 independently controllable electrodes. And that allows for active beam steering with reconfiguration of each of the elements. An interesting feature of active metasurfaces is that all metasurfaces, passive and active, are non-ideal when you actually fabricate them. And an interesting thing about active metasurfaces is that you can use inverse design to optimize the properties. For example, if you want to build a beam steering device, you want to avoid the undesirable side lobes that are shown at the lower left from a conventional repeated linear phase gradient. By using inverse design principles to optimize the directivity, we can produce a non-intuitive phase gradient that in turn optimizes the beam directivity and suppresses the side lobes. So this is a powerful principle for active metasurfaces. They're tunable after fabrication. In addition to simply steering the beam, we can optimize the beam's properties. And while the different physical mechanisms for permittivity tuning vary in their characteristics, this general principle can be applied to all of them. The active multifunctional metasurface that I showed you earlier, in addition to beam steering, was used in the same identical chip to form a parabolic phase gradient, whose curvature was varied according to the precepts of the lens maker's equation, to produce a reconfigurable lens with an electronically tunable focal length, which you can see this is a reflection mode lens, and you can see the focal point above the active metasurface plane in the simulation and the experiments below. This is quite a high numerical aperture lens, by the way. So now let's consider going beyond slow, what we call quasi-static reconfiguration, where we reconfigure maybe slowly from one state to another to create a different spatial phase gradient. And note that if we, at RF frequencies, we start with a carrier band and we impress upon it a signal, we can actually multiplex multiple signals on a same carrier band by and produce multiple signals by a frequency transmission, via modulation, time modulation of the RF transmission. And that's because we can drive electronics at RF frequencies to precisely tailor the temporal waveform. This principle was carried out in a very elegant fashion to perform not only spread spectrum multiplexing, but also non-reciprocal beam steering, which requires careful control of the temporal waveform. So what are the possibilities at optical frequencies? So we wrote a perspective paper about this a couple of years ago. And of course, the challenge at optical frequencies is that we cannot directly modulate the permittivity at a few hundred terahertz because we don't have electronics that's that fast. So we have to find other ways to do this, modulating the permittivity at lower frequencies. But we don't have to modulate at the carrier frequency. We just need to modulate at a frequency that can be separated from the carrier frequency. And because modern laser systems have narrow line width, that is, I'll show you in a minute, that can be possible. Okay, so imagine you go to Starbucks this afternoon and you sit down, and in Starbucks, many people are sitting working on their laptops. Each of them is communicating with a Wi-Fi node in the Starbucks, and they each have an independent signal that's clearly separable from the others. It's carried at a slightly different frequency. So the question is, maybe a decade hence, what does Starbucks look like in 2034? Well, I'm going to somewhat provocatively suggest that one possibility is that the signal is carried not by an RF, but by an optical waveform. We can look forward to either fast modulation of LEDs, the current version of Wi-Fi, or possibly even the advent of laser lighting, as we see that laser lighting is entering in some commercial lighting fixtures. So what that means is that if we have an ability to multiplex signals onto an optical beam, we could perform the same sort of ultra-high speed wireless communication using optical beams. So let's imagine how that might happen. So as I've described, quasi-static modulation can allow us to reconfigure the spatial phase gradient of a metasurface, as shown on the left. So if we now look at a map, a phase space of time and position, you can see that the effect of reconfiguring the phase gradient is to steer a beam at a different angle, which implies that we're imparting a parallel momentum to that beam. It's a tangential momentum shift. Now, let's instead imagine that we had a metasurface and we did not produce any spatial phase gradient. This phase is identical at every pixel in the spatial domain, but we now produce a time-varying waveform that produces a frequency shift that's discernible from the carrier optical frequency wave. So then that produces a frequency shift at the same angle. Conversely, we can now combine the two together and produce both spatiotemporal phase gradients, or space-time modulation, enabling both momentum and frequency shift to access any point in this frequency parallel wave vector phase space. And that's just the first experimental implementation of that we recently developed, and it will be coming soon to you in Nature Nanotechnology, perhaps by the end of this month. So this is a metasurface in which we impart a periodic spatial phase profile, in this case, a diffractive switching element that produces two diffractive lobes with different steering angles or parallel momenta. But we also produce a temporal phase gradient. And in addition, we can produce phase offsets between the two. So the metasurfaces look like this. They're very similar to the ones that I showed you earlier. In this case, the major difference is that we have carefully allowed the electrodes to be driven at sufficiently high frequencies to do space-time modulation. And in the experimental configuration here, what we do is to drive the metasurface now with an arbitrary waveform generator, which has a bandwidth up to the gigahertz range. We conduct experiments up to about 10 megahertz in this case. And we record now the reflected wavefront from the metasurface onto a photodiode, and we analyze not only its position, but its spectrum. In addition, the spectrum analyzer can be fed back to the arbitrary waveform generator with an optimization algorithm. So for example, you can see at the top a non-ideal device that should produce a single sideband, produces a sideband at 1 megahertz with a sine wave, but because the metasurface is ideal, we get a spurious sideband at 2 megahertz. Very similar to the inverse design spatial tuning that I showed earlier, we can also now produce a inverse designed waveform to suppress sidebands other than the one that we explicitly wish to make. So now we can go further and we can drive our diffractive elements in phase, in which case the beam is scattered specularly at normal instance, and we produce one beam at 1 megahertz. We can also now adjust the driving electrodes to be driven out of phase at 1 megahertz. And now we produce a beam only or primarily in the first order. There's a little bit of 0th order beam because we didn't do the optimization here or the suppression of the 0th order. But you can see it's pretty good in the measurement on the right, and the entire frequency polar angle plot is shown here on the right in both the calculation and in the measurement. So you can see here the steered beams at 1 megahertz. Using this general principle, we can go further. So for example, suppose we had 5 harmonics that could be generated. We could create a situation where we steer the 3rd and the 5th harmonic, as shown on the left, and we steer them at the +1 and -1 diffracted orders. You can see that in the calculation and the measurement. Or we could conversely produce a waveform that allows us to steer all 5 harmonics. Or you could, for example, show that we could steer the 2nd and 3rd harmonics and speculatively reflect the 1st, 4th, and 5th. So this is sort of a proof of concept of this general principle of harmonic beam steering. So we can, in principle, now steer. This is simplest realization showing we can steer beams at different frequencies at different angles. And to show this that in a way that allows us to steer at more arbitrary angles, we've constructed a 32 electrode active metasurface that illustrates the overall space-time drive that allows for space-time beam steering at multiple angles. So now I want to shift gears. Everything I showed you so far was described in reflection mode. We also are very interested in transmissive metasurfaces that can be cascaded to perform cascaded functions. Currently, we don't have active metasurfaces with high optical efficiency and reconfigurability, so we need to find a way of doing this. We know that lossless or low-loss dielectric materials can be used to make high-efficiency metasurfaces. To make active metasurfaces, these materials will have small index modulation, so we need to learn how to design high Q structures. So high Q structures have been investigated by a number of groups, including the Dion group, here shown in 2020, a guided mode resonance structure that was reported with a Q over 1,000. This is a fixed or so-called passive guided mode resonance structure, which guides in one dimension. The design from the André Alou group, shown on the right, non-local quasi-BIC metasurface design, has a slightly lower Q factor, but allows for 2-dimensional wavefront control. This one also doesn't feature a sort of arbitrarily reconfigurable type structure. So we began investigating dielectric high Q transmissive metasurfaces. And these consist of a very familiar motif for metasurface researchers, which is high-index silicon blocks, nanoblocks on a silicon dioxide substrate. And by carefully adjusting the blocks so that they support a hybrid Me mode, a hybrid of an electric dipole and octopole resonance, they support a high Q local resonance. This is shown in the spatial mode profile. You can also see the very flat dispersion relations for both TE and TM polarization, which indicates a quite localized mode. It's not quite localized to a single nanoblock. You can see it's spread over about 3 nanoblocks, but it's not like a photonic crystal mode or a block-like mode in which the mode is spread over the entire aperture. So we've fabricated these metasurfaces and shown that they can exhibit Q factors in the range from about 200 to 700. Other devices made in a 2-dimensional format showed Q factors over 1,000. And this also illustrates that we can steer along 2 orthogonal azimuthal angles. And that's important because that allows us to, in principle, steer in 2 dimensions. These type designs allow for simultaneously achieving high quality factor and relatively high numerical aperture. That allows us to make meta lenses that are, in principle, reconfigurable with index modulation that have high quality factor. With regard to index modulation, one mode of doing this is by thermo-optic index modulation, and we illustrate on the left a potential configuration in which resistively heated bars of silicon nanoblocks could be arranged in a spatial phase gradient to steer a beam. And so our simulations indicate that diffractive efficiencies as high as 50 to 70% can be achieved, and transmission efficiencies between about 5 and 10%. This is an illustration of early work on tunable thermo-optic high-Q dielectric metasurfaces. You can see here the designs illustrate thermal isolation from the substrate and thermal isolation of the elements from one another, which allows for microsecond time phase modulation with a phase range of over 300 degrees. So I want to finish by talking about conventional imaging and comparing that with metasurface imaging. And of course, you already know that metasurfaces are replacing, in some cases, conventional bulk optics, leading to a reduction in thickness and a reduction in weight. Conventional imaging with lens-coupled image sensors involves large sensor arrays and an aperture size that's matched to the lens size, which is matched to the aperture size of the image sensor, and the numerical aperture dictates the thickness or the focal length. And typically the field of view is limited, oftentimes apertured by the objective lens itself. So I want to introduce some recent concepts that have been studied in the area of imaging. Of course, metasurface imaging, in which phase gradients are allowed, as shown in this example from the Albert Pullman group at AMOLF, phase gradients that allow for spatial phase gradients that allow for edge detection. Lensless imaging is another concept. We can replace, in principle, the objective lens with any spatial filter that we can put in front of an image sensor, as long as we know its properties, and that can be it can be trained against a set of images. And then finally, single pixel imaging, in which a single pixel is used with a parallel array of transducers, in this case depicted as a digital micromirror array, in which an image is formed using a single pixel detector by serial detection through a variety of masks that are using the reconfigurable array. And these can be combined together into a concept that we introduce here of active metasurface lensless single pixel imaging. So this consists of an active metasurface, so there's no lens, and the only optical element is an active metasurface, which now acquires incoming scattered light from the object at different angles or parallel momenta. And the active metasurface can reconfigure itself to change its field of view dynamically. And we record a sequence of images temporally on a single pixel detector. Single pixel detectors, of course, are more limited in their capability than powerful image sensors, but in many instances where at wavelengths other than the ones where we have, for example, CMOS image sensors, it would be very desirable to be able to develop high resolution images in the far infrared or using single photon detectors. And this could be possible if we have active metasurfaces that work at those frequencies. So the primary mathematical concept here is that the image is represented as a convolution of the far field scattered object intensities with the antenna scattering factors of each individual antenna and a reprogrammable array factor. Of course, in an active metasurface, in principle, we can reprogram each element of the array. And that allows us to produce effectively a angular apertured field of view with complex angular aperture patterns with various configurations. So we collect a series of images, first, for example, the entire field of view, and then angularly selective collection over pre-programmed careful angular intervals to now produce measurements that look like the map in the middle of kx, ky intensity, and these can be computationally reconstructed to produce the image at the right. So we can now compare a single pixel active metasurface using the reconfigurable metasurface that I described earlier, and find out by simple calculation what the information limit would be for that metasurface compared with a CMOS image sensor, or for example, Texas Instruments style digital micromirror device, as I depicted in the first slide about single pixel imaging. And interestingly, because the pixel size of active metasurfaces can be made smaller than the pixel size of a CMOS image sensor, the achievable resolution can actually be higher. So if we use a ground truth image, this is the Canadian National Tower in Toronto, you can see the relative image resolutions that are achievable, primarily limited by the pixel size in this case. So active metasurfaces could also be used to modulate and produce spatial phase gradients, and to do so in multiple directions and at multiple spatial frequencies. By taking 2 measurements at each point and performing a kernel convolution, we can use a single pixel device now to produce an edge-detected image. Of course, there are different possible active metasurface platforms. I described those at the beginning of my talk, such as digital micromirror devices, liquid crystal devices, field effect carrier modulation like the ones I showed you here, or, for example, electro-optic devices that a number of groups are quite interested in. And the recoverable information is going to be limited either by the image acquisition time. For example, liquid crystals are reconfigured relatively slowly at the millisecond range. Electro-optic devices could operate in the nanosecond to picosecond regime. And then, of course, the overall signal to noise is dictated by the optical efficiency. And by acquiring sequential images, we could use a relatively fast device to cumulatively, in the same time, produce an image similar to that to a slow device, but with many different reconfigurable elements forming the computed image. Okay, so I wanted to just give a brief intermezzo. I know I'm very short on time here. And to mention, as many of you know, I and our group has had an initiative to develop active metasurfaces in space. And this, of course, is a double entendre because now we're talking about outer space rather than physical space. In other words, to build a light sail spacecraft using radiation pressure propulsion. And I wanted to just give, I can't possibly cover this entire subject here, time doesn't permit. But for those of you who are following this field, I simply wanted to alert you about some new results from our side. I look forward to hearing about other results from other teams. We've developed a extensive model that shows the dynamic stability of radiation pressure propulsion. There's a recent paper in Nature Communications that details this, showing that an active metasurface is not only shape stable, it can maintain its a light metasurface light sail can not only maintain its shape, but it can also ride on the beam. That's not an obvious concept because a weakly focused Gaussian beam with a flat surface in its radiation pressure interaction leads to an unstable beam riding configuration. But by using appropriately designed metagratings to produce restoring torques and forces, it's possible to make a beam riding metasurface. We've also conducted recently direct radiation pressure measurements for light sails that have allowed us to interrogate directly the optical forces on these structures. And I don't have time to tell you much more about it. There's lots of exciting experiments going on. I will mention that we have also been looking ahead to think about what an actual spacecraft would look like. And this is sort of an artist's conception of an actual spacecraft. This is a spacecraft that weighs 1.5 grams, and it's made of a 100 nanometer thick silicon nitride membrane that's 4 meters across. And it employs many of the devices that I've introduced to you during this talk. For example, it has an optical aperture in the center that transmits a short wavelength laser frequency beam using an active beam steering element. The circles to the side of the center aperture are also lensless cameras. Because the light sail needs to be two-dimensional, we cannot carry bulky lenses or even metasurface lenses that have a finite focal length. So these concepts that I've described in this talk, while of general interest, are also of interest for light sail spacecraft. So this is work that's been done by a talented team at Caltech, specifically recently by Lior Micheli, Mike Kelsenberg, and Ramon Gao. And I finally want to put up my concluding slide and thank again the talented team who made the work possible and the sources of support who supported us in the work. So I'd be happy to take a couple of questions if there's time.